Hello class, and thank you for watching. In topic 2.9 logarithmic expressions, you will learn how to evaluate a log expression without the use of a calculator. Now, let's begin by first defining what a log function is and what a log expression is. Now, the equation y is equal to the word log base b of x. This is the notation that we use to represent the log of a value. Now, the conditions here is that the value of x has to be a positive number, can never be negative. The base has to be a positive number that is not equal to 1. Now, this part right here looks very familiar to the previous lesson that we did on exponential functions. The reason for that is that a log is actually the inverse to an exponential equation. So what that means is that we can apply this concept that the inverse to a log is the exponential equation by stating the following, that this y equals log base b of x is going to be equal to the base of this expression. So this base right here, I'm highlighting in green, raised to this power of y, and that's going to equal to x. So if I get this base b, raise it to the power of y, that's going to equal to x. So let me highlight this. So this base corresponds to that. This value of y corresponds to that one right there, and it's going to equal to this input value that I'm highlighting in purple. Okay. So in order to evaluate like something like this, what I'm essentially looking for, again, what this is going to equal to is the exponent that I need to raise this base so it equals to this value that is in my parentheses, so the value of the log. Now, if I replace the notation y equals with f of x, then this just simply is a function. F of x equals log base b of x. That's how we read this. So again, let me write down how we read this, is the logarithmic function with base b. So this notation here, I'll write it over here on the far right. That right there is read as the following. Log base b of x. Now, before we go into how to evaluate this without the calculator and correlating the definition to its exponential equivalency, let's talk about two very special logarithms. The most common logarithmic function is the logarithmic function with a base of 10. Okay, so remember these values of b, the basis is going to be any positive number that is not equal to the value of 1. Now, if the base is 10, so where we have a log with a base 10 of some input value x, this is referred to as the common log. And the normal notation for such a log when our base is 10 is just this notation here. We have a quote-unquote invisible 10 that is used instead of the actual number 10. But that only happens again when the base is 10. If the base is any other number other than 10, then that said number has to be actually be written again down here to represent that base. But this is because it's the most common one. Base 10 is the most common base. The universal notation for such a situation is to simply write the log of x with an invisible 10 right there. Now the other, not common, but the other famous log is the natural logarithmic function when the base is Euler's number e. When our base to our log is the letter e, or the number, remember that's approximately 2.71. So log base b of x. The universal notation for such a situation like this is to use the letters L, N, not an I. This is not an I. I cannot repeat this enough. This is the letter L, L for log, and N for natural log. So the notation when we're using the natural base e, is to write the natural log. I know the letters are backwards from the acronym natural log, and you would think that we would use NL for the acronym, but in this situation we use L for log and then N. of x. So we end up with the natural log of x. And that's the notation when the base is e. So these are, again, special logs with base of 10 and a base of e, and the universal way of writing such a situation when our bases are those two specific values, okay? Okay, now let's return again to the original definition. Now, before we're able to evaluate a logarithmic function, again, we have to be able to use its definition and able to rewrite every logarithmic function into its exponential equivalent form. The exponential equivalent form is going to help us be able to determine what the value of a log function is without the calculator. So because, again, let me go back up here, because identifying the value of a log base b of x equals to y is equivalent to getting this base, raising it to this power of y is going to equal to x, we're going to practice rewriting our log function into its equivalent exponential form. So let's look at this first example right here, okay? To write this example into its exponential equivalence form, we begin by looking at the base and finding the base. Well, the base of our log is 5. So what we're going to do to this 5 is raise it to the value that the entire log equals, okay? So this entire thing equals to 5. So the exponent to this 5 is going to be the number 2. So it's 5 to the second power, and what it's going to equal to is this value right here that is not in parentheses. Normally it's in parentheses, to the value of the log itself, which is x. So the equivalent form of log base 5 of x equals 2 is 2 to the 5th power is equal to x. So if I read this and write this the other way around, let me get a thinner pen here. Let me do it 1. Log base 5 of x equals 2, as you can clearly see right here. I start by getting this, equaling it to that value, raising it to this value of 2, and then equaling to that value right there, okay? And this would be the equivalency of taking this part right there, or this part right there. Now, the reason that this is important is because using this definition, as we'll see in later examples, we can use this to evaluate and figure out what the log base of any value of x is going to equal. Let's now look at this next example. So this right here, we have the common log. Notice that there is no base indicated because this is the common log. We have an invisible 10 right there. So let me rewrite this and write first that the log, let me get a different pen. Get me a thinner pen. So let's write this as the log base 10 of 1000 equals 3. Now, if I'm going to write this again in its exponential form, find the equivalency in exponential form, what I'm going to do is start with the base, which is 10. I'm going to raise it to this power of 3, and that's going to equal to this value that's in the parentheses, which is the 1000. And this again correlates to what a log function is doing. A log function, and the value of a log function, this right here, is equal to 3, because if I get 3 and I raise it to the third power, that has to equal to 1000, since 10 times 10 times 10 equals 1000. So that's why the common log of 1000 equals to 3, because log base 10, yes, of 1000 equals to 3 because of that reason. And what we're doing is using this equivalency to determine again what the exponential form is. Let's now evaluate and let's write the equivalent form of this natural log of x is equal to y. Well, first of all, again, the natural log of x means that we have a log with base e of x. So think about this function again like this, that there's this invisible e right here on our function, on our base, okay? Which again will change the ln to log base e of x. The exponential form of this again begins with this base of e raised to this power of y, and that's going to equal to x. So this is the equivalent form to log base e of x is equal to y. Now for the example 2, let's go backwards and let's write each equation in its equivalent logarithmic form. Because these things are equivalent to each other, these two definitions here, these two notations are equivalent, I can obviously go from left to right, and I can then also go from right to left. Given an exponential equation, I can write it into an equivalent logarithmic form. So let's look at the example that we have down here on letter A, for example 2. So in order to write this into its exponential form, first we're going to write the log and the base. Well, the base here of our exponential equation is 12, because that's what has the exponent. 12 has the exponent of 2, so our base is going to be 12. Now, what's going to go inside this value? Well, what's going to go inside this value is going to be this value of x, that right there. And the log base 12 of x is equal to the exponents to our base. That's again what the log function is doing. The log function of x is the answer to this is going to be the exponent that we have to raise this base, in this situation 12, in order to get this value of x. So the numbers right here for the values of x would have to be 12 or 144, because 12 to the second power, and then 12 to the third power, whatever that number is, and then 12 to the fourth power, whatever that number is. Those are possible values for the value of x, okay, which in this situation would have to be 2. So log base 12 of x equals to 2 is equivalent to that right there. Let's now look at example B. For example B, again, to write this in its logarithmic form, we're going to get the base, which is b to the third power. So the log base b of the value that we want is going to be 8. Now again, the answer to this, the log base b of 8, is equal to the exponent to our base. And since that base exponent is 3, the log of base b of this value of 8 equals 3. So this would be the equivalent form to that exponential equation of b to the third power equals to 8. Now finishing off this type of examples, let's write this in its logarithmic form, this exponential equation, into a logarithmic form. So we're going to start by writing the word log and identifying the base. The base is e. Now this is a subscript, okay? It's again like instead of a power, it's like the opposite, it's in the bottom. And what we're going to put in the parentheses is what the value of the exponential equation equals to. It equals to the value of 9, so that goes right there. And the solution to this log base e of 9 is again the exponent to our base, and our exponent is the letter y. So this is going to end up equaling to y. And that is our equivalent logarithmic equation. Now, I can manipulate this. Well, it's fine to write your answer like this. Again, the more common way of writing, because we're taking the log of base e, is to use the natural log notation of ln. So ln of 9 equals to y. And I'm saying ln again to emphasize the fact that this is an L and not a letter I or the number 1. This is ln. N for natural, L for log. Okay, so we're taking the natural log of 9 equals to y. So this is the more common used notation. This is still good, all right? You'll get credit for that one, but this one is the more common way of writing it. Let's now apply again the equivalency of a log with an exponential expression. Now, we can apply this again to evaluate log expressions without the use of a calculator. So let's look at example 3, letter A. So here we're asked to evaluate the log without a calculator. So log base 2 of 16. Well, let's say that it's going to equal to some value y. So we're trying to figure out what the value of y is of this. Now, obviously, this right here is kind of difficult to do it in this notation. But because this is equivalent to an exponential expression, an exponential equation, better said, I can rewrite this into its exponential form and then solve this value, solve what this is going to equal to by its exponential equivalency. So to write in exponential form, let's practice yet again that skill. We're going to start by looking at the base of 2. It needs to be raised to this power of y, this value that I'm looking for, and it has to equal to 16. So figuring out what this value of y in this equation up here is the same as trying to figure out the value of y in this equation down here. And this notation of 2 to a power equals to 16 is simply asking us how many 2's do I need to multiply until I get the value of 16. Well, trial and error right here. Well, I know that's 2 times 2 gives me 4. If I multiply another 2, so three more 2's, that's going to multiply this answer by simply 2 more. So 4 times 2 would be 8. If I multiply another 2, I multiply another 2 yet again. So this would be 16. So the number of 2's I need to multiply until I get 16 has to be 4. So 2 needs to be raised to the 4th power to get this value of 16. So that means that this exponent has to be 2, which again correlates back to this, which means that the log base 2 of 16 has to equal to 4. So this is our answer. The log base 2 of 16 equals to a total of 4. Let's now look at example B. For example B, first of all, this is the common log. Notice that there is no base indicated here because that base is 10. So we have the log, the common log, so log base 10 of 1,000, and we want it to equal, we want to figure out what it has to equal to something. So this is what we're trying to do. Figure out what that number is going to be, and let's call that number for right now y. Now, rewriting this into exponential form, that would mean that this base of 10 would have to equal to this unknown that we're trying to find, y, in order to get, again, this value of 1,000. So how many 10's do I need to multiply till I get to 1,000? Well, I know 10 times 10 is 100. So if I multiply one more 10, that would multiply 100 by one more 10, which would be 1,000. So I need to multiply 3 10's to get 1,000. So that's 10 to the 3rd power. So that means that this value of y is equal to 3. So the common log of 1,000 equals 3. So this is your answer. Let's now look at a different example, example C. It's a little bit twist to this concept right here. This again, we're trying to evaluate the log base 7 of 1 over 49. What is this going to equal to? So let's say set it to say that's going to equal to some value of y. Now its equivalent exponential form will get the base of 7, raise it to this power of y, and it has to equal to 1 over 49. Okay. Now the key thing in focusing on here is this number of 49. I know that 7 times 7 equals 49. So that means that 7 to the positive 2nd power equals to 49. But since I want the reciprocal of that, 1 over 49, well, I have to recall my negative exponent property. My negative exponent property states that if I have a base that is raised to a negative exponent, then that's equivalent to getting the reciprocal of the base, so 1 over b, and that changes the exponent to a positive value, okay? Now, of course, this also works backwards. If I have a base with a positive exponent, getting the reciprocal of the base, 1 over b, changes the exponent to the opposite of what it currently is. So positive becomes negative and vice versa. Negative becomes positive. This notation is just simply stating again that if I get the opposite of whatever I start off with, then it's going to simply give me the reciprocal of this. Stating that if 7 to this positive 2 is equal to 49 over 1, then that means that if I change the exponent to the opposite, negative 2, this would give me the reciprocal of 49 over 1, which is 1 over 49. So I would have to raise 7 to the negative 2 power in order to get this value of 1 over 49. Okay, so this value of y has to be negative 2, which correlates back to the original log, that the log base 7 of 1 over 49 ends up having to equal to a negative value, negative exponent. So that's your answer. Okay, now let's look at this example, example D. So again, we want to evaluate the log base of 25 of 5, log with base of 25 of 5, and we want to know what this equals to. So let's say we're going to set it equal to some number, and let's call that number again y. Now, the equivalent exponential form of this would be that 25 has to be raised to some power of y to equal to 5. Well, in the previous example, we talked about having a negative exponent simply gives me the reciprocal of the value that I want. So if I have 25 to the first power, which is just 25, that would mean that 25 to the negative 1 would be the reciprocal of that. So 1 over 25. Now notice that this is not the case. It's not going to help us again in order to get this value, because I want to get 5. I'm not looking at the reciprocal of a product of 25s or a factor of 25. I'm looking at a number that's smaller than that. Now, when we're getting a base to a power and it's equaling to a smaller number to this original base, this is going to be the hint that the exponent we are looking for is going to be a rational number. So we're going to use is the rational exponent rule. So let me rewrite that one, okay, and let's review that. Rational exponent. A rational exponent states that if I have a base and I'm raising it to 1, and we'll say it's 1, equivalent of 1. So 1 over n, okay? We have a rational exponent, an exponent that is a fraction. This is equivalent to simply taking the indicated root n of that base. So for example, like in this example, if I have 25 and I raise it to the 1/2 power, that's the same thing as taking the square root of 25, which is obviously just going to equal to 5. Or if I have the number 8 and I'm raising it to the 1/3 power, that's the same thing as taking the third root of 8, and that of course equals to 2. So if I look at this example right here, the only way I can get this base of 25 to equal to a smaller number is that if I'm taking some type of root. Well, we already did it for you over here on the side. I am taking the square root of 25. That's the only way 25 can equal to 5, that if I take the square root of 25, which is the equivalency of raising 25 to the 1/2 power, okay? So that means that this exponent of y, this unknown value of y, has to be the fraction 1/2. And correlating that to the log, that means that the log base b of 25, log base of 25, not base b, but the log base 25 of the value 5 has to equal to 1/2. So this right here is your solution. Let's now apply this property and the previous property from example C to solve this one right here, okay? So here again, we want to evaluate the log of base 25 of this value of 1 over 5. So it has to equal to some value. Again, we'll call it y. So the equivalent exponential form means that 25 is going to be raised to some power. So it equals to 1 over 5. Well, from the previous example, we know that if I get 25 and I raise it to the 1/2 power, that equals to just the number 5. And from example C, we know that if our exponent is negative, so if this is equal to 5, then that means changing the exponent from a positive number to the opposite, negative number. So negative 1/2 will give me the reciprocal of this answer. So this would be 1 over 5. So using that, I now know that the exponent that I have to raise 25 to get the fraction of 1 over 5 has to be negative 1/2, which means that this value of y has to be negative 1/2, and that correlates again back to the original log function or the log expression, and that this would simply equal to negative 1/2 since we need to get the reciprocal. Moving on to the next example, here we want to get this base of 7, raise it to a power to equal to the square root of 7. Well, using again the fact that taking the square root of 7 this side over here is the same thing as raising 7 to the 1/2 power. Let me keep it in blue. 7 and raising it to the 1/2 power. The only way that 7 to the y power equals to 7 to the 1/2 power is if these exponents are equal to each other. This is referred to as the one-to-one property of exponents. 2 in blue. There we go, right there, okay? Which states this, that if I have a power raised to a raised to a power of x, and it equals to another power with the same base, but is raised to a different exponent, let's say y, the only way that these powers are equal to each other is if these exponents are also equal to each other, okay? Which means, again, that the value of y has to equal, again, to that. So the answer to this is that the log base 7 of the square root of 7 equals to 1/2. And this property is very, very cool, because if I think about it like this, that if I have, in other words, if I have two things that are equal to each other, I can apply this property. I can make this value of x be the exponent to some base b, and in order to keep it equivalency, that would mean that the value of y would have to be the the exponent to the same base b. So I can also do that. It's very similar again to the concept that if I get x equals to y, and I get the reciprocal of the left side, 1 over x, in order to keep it equivalent, I would have to get the reciprocal of the right side and write this as 1 over y. So a very cool property that we have right there that correlates again to this idea, and we can use it again to evaluate this log function. Moving on to the next example, letter G. The log base 3 of 1 has to equal to some value of y. So 3 to some value has to equal to 1. Okay. Well, we know that 3 to the first power is equal to 3. 3 to the second power will equal to 9. 3 to the third power multiplies again another 3 to that. So that will be 27. And then 3 to the fourth will multiply another 3 to the previous answer, which ends up equaling to 81. Okay. Notice that these answers, these values are getting smaller and bigger and bigger and bigger. Okay. They're actually moving further and further away from this value of 1 that we want to figure out. So we know that this cannot equal again to these numbers, and that can't equal to a negative, because a negative exponent, 3 to the negative 1, is simply just going to give me the reciprocal of having a positive exponent. So 3 to the negative 1 is 1 over 3. 3 to the negative 2 is 1 over 9, and then 3 to the negative 3 is 1 over 27, and so on and so on, okay? So let's think about this, okay? What power do I have to raise in order to get this value of 0? Well, if I'm increasing the exponents from 1 to 2 to 3 to 4, I'm simply multiplying another 3 to my previous answer, okay? And I want to know, how am I going to get this to 1? Well, let's look at this and let's think about this backwards. If I go from 81 to 27, I'm not multiplying by 3, I'm dividing by 3. And that is decreasing the exponent from 4 to 3. So I'm decreasing the exponent by 1. If I do this again, that 27 divided by 3, that's going to end up giving me 9. And again, my exponent decreases from 3 to 2. If I divide 9 by 3, that's going to again give me 3. And that decreases the exponent from 2 to 1, because I'm now only multiplying 1 3. I only have 1 3. And if I do this again and I get this 3 and I divide it by 3 again, that's going to end up equaling to 1. 3 divided by 3 is 1. And well, again, since I'm eliminating number exponents, that means that 3 would have to be raised to the 0 power, which again goes back to our exponent rules, our 0 exponent property, which states that if any base is raised to the 0 power, that is always going to end up equaling to 1. And this is just a way of understanding and defining why anytime I get any base raised to this power of 0, I always end up with 1. So the solution here, let me erase all of this because I don't need this anymore, is that the log base 3 of 1 is going to equal to 0. So the same thing must be true about this one, that the log base 7 of 1, that also has to end up equaling to 0, since 7 to the first power is 7, 7 to the second is 49, 7 to the third power, so on and so on, is going to be again 2 something. I'll look at that right now. So that means that if I go backwards and I divide this value, I'm sorry, this is 343. Dividing this by 7 gives me 49, and then dividing that by 7 gives me 7. And then when I divide 7 by 7, that's going to end up equaling to 1. So again, 7 would have to be raised to the 0 power. And again, that correlates exactly to this idea. That anything, the only way to get a base to equal to 1 is if that exponent to the base is always 0. Now let's use the previous example to evaluate and use basic log properties that involve the number 1. The first property is that if we have the log base b of b, so in other words, where these two values are the same, where the base matches, there we go, matches the value of that, the answer is always going to end up equaling to 1, because the only way to get this base raised to a power to equal to that exact same number is if that exponent is 1. So b to the power of 1 is equal to b. So for example, if we look at example A here, log base 7 of 7 is simply equal to 1. That's going to be our solution. This equals to 1 because 7 to the first power equals to 7. Similarly, again, to this example right here. This right here is going to end up equaling to 1. The notation here is that since they're using the natural log, ln, recall that that means that we have a log with base e of this value of e. This is what we're trying to evaluate, okay? And since the base and the value of the log that we want to take of are the same, that means that this has to equal to 1, because the only way that this is, the reason that this is true is that e has to be raised to the first power to equal to that value of e. So this raised to this power of 1 equals to that. Let's now look at the second property that involves 1. That property is the following. That property again correlates to what we just did in the previous examples on examples G and H. That if we have a log of a base of the value of 1, so we're evaluating the log of 1 regardless of what the base is, okay? Common log, natural log, base 9, base 2, whatever this base is, the answer always has to be 0, again because this base has to be raised to the 0 power in order to equal it to this value of 1. So for example, let's look at C and D. Let's start off with D first. The log base 8 of 1 has to equal to 0 because 8 to the 0 power is equal to 1. And the same thing with letter C. This is just a natural log. So our base is E. So regardless of what the base is, if we want to evaluate the log of 1, regardless of the base, the only way we can do that is if this thing equals to 0. And if we convert it again and apply it to its exponential equivalency, it makes sense because e to the 0 power equals to 1. This base e raised to that power equals to 1. So the only way to get this exponential equation to equal to 1 is if the exponent is 0 to the base. And then finally, we have the inverse properties of logs. The first property, again, given that b is a positive number not equal to 1, the log base b of b to the x, as you see right here, is going to end up equaling to x. This correlates again to the fact that it has to do again with this property right here of equaling to 1. This basic property of 1. Since this value right there is equal to 1, in this situation where we have an exponent, and we'll talk about why this works with a different property in a later chapter, is that in these situations we can clearly think is that since this right here is equal to 1, well, the only thing we're going to be left with is with this exponent that we have on this b. So for example 5, to evaluate a and b, that applies again to this property right here. Since the base and the exponent are the same, these two things are going to cancel each other out, and the only thing that's going to be left is the exponent of 5. So the log base 4 of 4 to the 5th power is simply the exponent of 5 to this base that we have here. And again, that matches to that right there. So letter B does the exact same thing. Since this is the log base b, log with base e of e to the x, and the base of the log and the base to this exponential expression are the same, they're going to cancel each other out, and the only thing that is left is the exponent of x. So that would be your answer. And the last property is this property right here, that if b is raised to the log with base b of a number equal to that number, then they're going to cancel themselves out as well. So this, let me get my highlighter instead, this and this is going to cancel itself out as long as the base to this exponent and the base to this log, which is in the exponent, match up. Then they essentially cancel each other out, and the only thing that is left is this value of x. So this x is the answer. So apply it again to example C and D. So in example C, we have base 6. The exponent to this base of 6 is all of this part right here, which is a log, but the base of the log is also 6. So the base of the log is also 6, and since those numbers match up, they essentially cancel each other out, and the only thing that's going to be left is the number 9. So our answer here is that 6, let me do it in black, 6 to the power of log base 6 of 9 is just 9. And it's true again if it's a log with base 6 or the common log, or if it's a natural log. You just have to again make sure that you read this carefully. Understand that the natural log is just a log where the base is e. But of course, again, like I've been mentioning in all this video, we use this notation instead of that notation. You just simply have to correlate that, and x to the 2nd power. So since this is the base to a log with the same base of e, those things are going to cancel each other out, and the only thing that's going to be left is this part right here, which is x to the 2nd power. So this equals e natural log of x squared equals only to the x squared parts. So that is your answer. All right, so that concludes our notes on this section, 2-point logarithmic expressions. Thank you again for watching. If you have any questions, send me an email or a message through Parent Square, preferably with Parent Square. And like always, again, thank you for watching, and I hope you have a great day. Goodbye.